Hi, welcome back to Enzyme Function and Kinetics. My name is Kevin Tokoph. Make sure to like this video and subscribe to the channel for future videos and notifications. All right, so one thing that I found in teaching this kind of stuff for Michaelis-Menten kinetics is that the most difficult concept to understand, or at least one of them, is what the Km is. All right, so the Km is this part of the Michaelis-Menten equation right here. Now, the Michaelis-Menten equation says that the initial rate of an enzyme, and that's when we're doing saturation kinetics, is equal to the maximum rate of the enzyme times the substrate concentration divided by the sum of the Km plus the substrate concentration. So we can ask ourselves, what is Km in words? We can express a formula for it. So what is Km? It's the substrate concentration required to elicit half of the Vmax. So what is the Vmax? That's the maximum rate of the enzyme possible at given conditions. All right. So the Km is the substrate concentration at half of the Vmax. Another way of saying it, substrate concentration at half of the enzyme's maximum rate. Okay, that's what it means verbally. What does it mean mathematically? Well, this Km, I just want to be clear to you, this is capital K. So capital K sub m is the Michaelis constant, and it's equal to k minus 1 plus k2 over k1. Now what are those? Well, these are rate constants, okay? The Km is Michaelis constant. That's a capital K, okay? These are individual rate constants, okay, on the right side of this equation. So the equation ultimately comes from when we have an enzyme plus a substrate in equilibrium with the enzyme-substrate complex, which gets converted to the enzyme plus the product. So K1 is this rate constant, K minus 1 is this one, and this is K2. So if we know these rate constants, if we actually knew what they were, we can actually take K minus 1 plus K2, divide by K1, and that gives us the Michaelis constant. Unfortunately, it's very difficult to determine individual rate constants. You can do it, it's just very difficult, all right? So there's other methods to determine the Km, and we're going to talk about those in other videos. But I mean, just knowing that it's this expression with rate constants, or that it's half the concentration of it's the substrate concentration required to give half of the Vmax, that really doesn't help us much. And in terms of when Michaelis and Menten made this equation through a derivation through steady-state kinetics, how did they figure out what the Km actually is? Now, what we're going to do is essentially a very simple proof to show that Km is in fact this right here. Okay, now the first thing we need to do is discuss what are the units of a rate. We have two rates here. We have an initial rate and a maximum rate. All right, so what are the units of rate in biochemistry? Well, hopefully you know that the units of rate, because a rate is a change in concentration per unit time, the rate ought to be something like molar per second. Okay, now in the top, the numerator, we have some concentration type of unit. In the denominator, we have a time type of unit. So you could technically use for the denominator seconds, minutes, hours. You could use millennium, right? For the top, you could use molar, micromolar, millimolar, nanomolar, okay? But for this, I'm just going to keep molar per second, even though they're not usually expressed that way, just for simplicity. So this could be molar per second. And that's the units of a rate, right? It could be micromolar per minute if you want it. But I'm just going to use molar per second just to illustrate the point, all right? What are the units of a substrate concentration? Well, the units of a concentration have to be something like molar. Okay, they could also be millimolar, nanomolar, whatever. But just for simplicity, I'm going to keep everything kind of consistent. I'm going to use molar. So this one down here is also molar. All right, so let me do this. So let me say for the units of Vmax, all right, or the units of V initial rate, excuse me, molar per second equals the units of Vmax are going to be molar per second. What are the units of substrate concentration? Molar. And then that's divided by whatever the units of Km are, plus, and then this is molar. All right? Now, here's the question. What do the units of this Km, and I'm talking about this right here, what do these units have to be in order for all of these to multiply and add together, essentially to give molar per second? What does this unit have to be in this context? Well, remember that if in any kind of expression with units, if you're going to add two things together, they have to have the same units. So you can look at it that way. So let's suppose maybe this is molar. Let's suppose the Km has units of molar. All right. So what happens whenever we put this together? Well, you're going to have molar per second times molar, and then what's molar plus molar? Well, the units are the same, so it's just molar units. And then hopefully you can see that this molar cancels out, and sure enough, you get the units of the initial rate, molar per second. Now that's a really important observation. Km has units of molar. Okay, now in anything you've dealt with in chemistry up to this point, what typically has units of concentration or units of molarity? Well, the only thing I can think of is concentration. So let's postulate something or hypothesize something. Let's say Km is a concentration. Okay, I don't know that right now, potentially, but let's suppose Km is a concentration of substrate. All right, that's something that would be reasonable. It has units of substrate concentration. So why don't we just suppose it does? Km has units of concentration. So let's suppose Km is a type of substrate concentration. Now, it is a constant for a given enzyme, but it could be a substrate concentration that is a constant. Okay, so let's just assume that. Okay, now the way you determine what Km is because you determine that Km it could potentially be a substrate concentration. What you're going to do essentially is substitute in for Km substrate concentration, because I'm going to assume that the Km is a substrate concentration. It's some kind of substrate concentration. Okay? So the initial rate is the Vmax of the enzyme times the substrate concentration. And remember, I'm going to assume, just to test it to see if Km, I'm going to assume it's a substrate concentration. So plug that in here. Okay? So this right here, this is essentially Km, but I'm putting it as this. All right? And then this is adding on to it another one, concentration of S. All right? So what happens when I do that? Well, the numerator doesn't change. It's Vmax times the concentration of S. Now remember, technically both of these have coefficients of 1. So when I add these together, I'm actually going to get 2 times the concentration of S. Now, if you already knew what Km was, you may be able to see where this is going, but notice that the concentrations of S's here cancel. And so that's going to leave me with the initial rate being equal to Vmax over 2. Now, another way you can write this is literally 1/2 the Vmax. And that in and of itself is a very important result. So again, when did we just determine that the initial rate is 1/2 of the Vmax? So we're saying the initial rate is equal to 1/2 of the Vmax. Under what conditions did we just determine that? Well, we determined that literally when the Km is equal to the substrate concentration, right? Because I substituted Km in for substrate concentration, and this is the result that happens. So it turns out that literally when the substrate concentration is equal to the Km, the rate is half of the maximum rate, or the initial rate that you observe is half of the Vmax. Okay, and that's literally the proof that Km is equal to the substrate concentration at half the Vmax. All right. And for any enzyme at a given set of conditions like pH or temperature, the Km is a constant. Okay? Now, yeah, you can say Km is K minus 1 plus K2 over K1, but in reality there are other better ways to determine what Km is. And we're going to discuss a few of those in some of the videos to come. One of those is going to be something called a Lineweaver-Burk Plot, which is something you're probably going to discuss in your biochemistry course. You can also do something called a Haynes-Wolff plot. It's another way to do it. And you can also estimate the Km graphically if the Vmax is relatively known. Okay? So this essentially is the proof that the Km, or the Michaelis constant, is the substrate concentration at 1/2 of the Vmax. So I hope this video gave you some intuition, hope it helped. Make sure to like this video and subscribe to the channel for future videos and notifications. Thank you very much.